Okay, so this video is going to cover PNP transistors. Now, often in an intro to electronics course, we would mainly look at NPN transistors or NPN BJTs. That gets most of the emphasis. And then later on in more of an advanced course, we'd get into the PNP transistors. But we're going to slightly just touch on them for now. Now, simply recall the semiconductor makeup of the NPN versus PNP and the current notation for the NPN and the PNP. So for the PNP, we have some current that goes through the emitter to the base, and that allows for some collector current to flow from emitter to collector. Now, the notation that we use is fairly similar, which is why it can be a little bit confusing, which is why most of the emphasis is on the NPN. Again, we're going to have the collector current equal to beta, which is the gain, times IB, and the collector current is equal to alpha times IE, or the emitter current. Pretty easy to get confused. And one of the key things you have to look here is in the schematic symbol, this arrow, whether it's coming out or going into the base. Now we can define some Shockley-like current equation for the emitter, and it's going to look similar to the NPN, except notice this negative sign here for minus VBE. Similar thing for the base, we get this minus sign, so really take note of the minus sign. There's a lot of minus signs in the analysis. Now we keep a similar notation for VBE and VCE, like the NPN, but it's flipped. So what we can do, we can look at the characteristic equation. So we have, again, our input right here where we look at the base current and VBE, but because we're flipping things, what you might see in the graph is horizontally, you'll get minus 0.6 volts for VBE. Similarly, for the output characteristics, we're looking at the collector current and then VCE with different base currents. But again, notice VCE is negative now, and we get this negative 0.2 for the saturation region, and to the right of minus 0.2, so the further negative we go, we get that active region. So again, very similar, lots of negative signs. But let's consider a circuit, and we're going to consider a PNP transistor. So let's just denote that here, where we have a beta value of 100. And if we assume that the PNP is in the active mode, well, we'd see that VBE is equal to minus 0.6 volts, or VEB is equal to 0.6 volts. And again, that's coming from this input characteristic right here. So what we're going to do is simply say that if we have a 5 volt source right here, and we are active, and we have a 0.6 volt drop right here, what we can say is that this base is going to be equal to 4.4 volts. Now, if that's the case, we can define a base current simply as 4.4 minus 1.5 volts divided by this 50k ohm resistor right here, such that our base current is 58 microamps. Now, if the base current is 58 microamps, and we know that beta is equal to 100, then we can say that the collector current is equal to beta times IB, or 5.8 milliamps. Now, if we try to check our work, and we say that the collector current is 5.8 milliamps, and we have a 10k resistor here, that would mean that VC is equal to 58 volts, which is a little bit odd because VE is equal to 5 volts, which would also say that VCE is positive 53 volts, and we know right here we'd really like to have a negative value if we're in that active region. So things don't really make sense. So maybe we're not in the active region. Let's consider being saturated. So we're going to say that VCE is minus 0.2 volts, or VEC is 0.2 volts. Now, if that's the case, we have, again, that 0.2 drop from VEC. So VC would be 4.8 volts. And that would allow the collector current to be 48 milliamps. Our base current still would be the same at this 58 microamps. What we can say is that we have beta, which would be a saturation version of beta, which is equal to IC divided by IB. So we could also say that this is 480 microamps. So we would have 480 microamps divided by 58 microamps. So our saturation beta would be 8.275. So let's go into the simulation to see what we get. And we set up a circuit. Unfortunately, the best fit I could find was beta being equal to 77. So we're not going to get the exact same answers, but it's going to be pretty close. Now if we look here, in the green we have our base current, which is about 60-ish, a little over 60 microamps, and our collector current, which is about, call it 490 microamps. So 65 and 490, pretty close to 58 and 480. So this would validate what we just went through. And we can confirm that we are in the saturation mode. Now in general, NPN transistors are good for sinking current and PNP transistors are good for sourcing current. Again, we'll see more of this in the advanced electronics playlist a little bit in the future, but we commonly see NPNs used in amplifiers, logic gates, fast switching applications. Now a PNP transistor, or a set of them, can do this, but the question really depends. Should you do this based on cost, speed, performance, etc.? So PNPs are still used. They're still worthwhile considering, but they're more limited and more advanced. Now, the next two videos will be large signal and small signal analysis for BJT models. We're going to return back to the NPN transistor, and we'll see you in those videos. Thank you for watching.